Hi everyone, I'm Basu and I worked with Yatong and Kyle, and today we'll be talking about privacy in social network graphs. So our initial motivation is this paper by Seish, and he says that triangle-rich complex networks lose out on a lot of low-degree triangles in low-dimensional embeddings. So we ask whether it's possible to turn this into a privacy result. Does the fact that we are losing out on detailed structure while extracting some information mean that we are satisfying some level of privacy in some setting? So what's our specific approach to this? So as I said, Seish suggests that low dimensional embeddings cannot preserve a large number of triangles incident on low degree vertices. So armed with this knowledge, we try to artificially construct graphs that we hope will induce poor performance by these methods. So the first kind of graph is a proxy for a real social network. These are sparse graphs, but these have lots of triangles. However, because they're sparse, most of these triangles are incident on low degree vertices. The second kind of graphs have fewer triangles overall, but they are all tightly knit. And so most of these are incident on high degree vertices. So what's our contribution? So we hope that the graphs of the first kind will lose more triangles and graphs of the second kind will lose fewer triangles. So essentially we are saying that graphs with very different number of triangles will end up with embeddings which have comparable number of triangles. And we hope that this is the first logical step in establishing an epsilon delta differential privacy argument for a similar setting. And we hope that a first step that we do is sufficient, that is observing triangle loss across two types of graphs. For empirical validation, I move on to Yatong, who talks about SVD.
The intuition for the SVD-based method is that we take the original network and map each node into a lower dimensional vector, and then reconstruct a perturbed graph based on these vectors. Here, the lower dimensional vector for each node is the corresponding row in the lower dimensional Laplacian matrix of the graph. By doing this embedding, we perturb the edges, and we would like to see if this method can preserve some properties of the original graph, like community structure, number of triangles in the graph, and the degree distribution. The parameter in this algorithm is the dimension of the lower dimensional space. We first run our algorithm on the real Facebook dataset. This corresponds to the type 1 graph that Basu introduced before. We can see that the original graph has some community structure by looking at its adjacency matrix, and the degree distribution satisfies the power law. After embedding it into a lower dimensional space, the new graph loses the community structure, and it loses around half of the triangle counts. And there's a shift for the degree distribution as well. If we further decrease the dimension, we'll get a less accurate approximation. We also run it in a stochastic block model with much higher in-group probability. This corresponds to the type 2 graph mentioned before. For the original graph, we can see a clear community structure with strong in-group connection. After embedding, we can see relatively clear community structure of the new graph, and it loses only around 1/3 of the triangle counts. The shape of the degree distribution is similar as before. Overall, compared to type 1 graph, we can see that type 2 graph is better at maintaining the properties of the graph in terms of community structure, triangle counts, and degree distribution. However, it might be because of the specific choice of graph you're studying. Next, let's move on to the network node-to-vec method.
So in this method, we pass the original graph to the node-to-vec graph embedder. We then compute pairwise dot product similarities and use a neural network to classify these similarities as being an edge or not. From this, we can reconstruct the graph as represented by the embedding. Now in complete graphs, you'll notice that this method preserves the structure and the degree distribution of the graph. But complete graphs are a simple type of graph, so let's see what happens on a more complex type. We consider a random partition graph, which allows us to specify groups in the graph and give probabilities for edges between nodes in the group and out of the group. You'll notice that after performing our method, connectedness of the groups increases, but the intergroup structure is completely lost. In addition, the degree distribution is skewed towards lower degree nodes. Now, to get a better idea of where we're losing triangles, we compute two quantities: absolute triangle loss and relative triangle loss. Absolute triangle loss is the sum of the difference in triangles on nodes of the same degree, and relative triangle loss is the average percent of triangles lost on nodes of the same degree. From this, we can verify that we are losing triangles on low degree nodes, but we also see that on high degree nodes, the number of triangles increases, which suggests this method underestimates the intergroup connectedness and overestimates in-group connectedness. In conclusion, our results agree with Sesh's work, and we believe that some indistinguishability result can be demonstrated for certain types of graphs when processed with our methods.